Welcome to the lecture on fundamentals of MIMO wireless communication. In the previous lecture, we have discussed the Rayleigh fading condition, which gives rise to the autocorrelation function, which gives a Bessel function of the first kind with 0th order, and we have also discussed what is the meaning of coherence time. We have also discussed the slow fading and fast fading conditions and how they would arise in different operating conditions as well as for different communication systems. In the last lecture, we were just trying to compare the different situations of fast and slow fading, and we have also said that if there is fast fading, the signal would fluctuate faster than the channel condition. That would require a better receiver to be built or even better transmitted signal design. At the same time, we should also try to understand or have a fair idea about what is the problem when there is slow fading. The advantage of slow fading, of course, we have mentioned that when there is slow fading, that means signal rate is faster than the rate at which the channel is fluctuating, or the signal strength is more or less constant during the symbol duration. That is one view of the whole thing. The other view of the thing is the channel is fluctuating at a very slow rate. Okay. So, if I would draw another channel which fluctuates at even a slower rate, a channel which would fluctuate at even a slower rate, right. So, what I have tried to draw is I have tried to draw the other side of the coin, means I could have drawn the signals going up, but what I mean to say by this particular picture is with slow fading, as the signal rate remains constant during the symbol duration, on the other hand the signal actually remains quite constant during the symbol duration. What does it mean? That once the signal strength falls below a certain threshold, suppose I have a certain threshold of operating point. If the signal strength falls below this particular threshold, for it to come back above the threshold, it takes quite a lot of time. Now, why this threshold is important? Because we would require the received signal strength P received at distance d we had calculated to be greater than a certain threshold, right. Only once we are able to do this calculation, means this calculation is important for coverage probability, this is important for bit error probability. That means provided the level the signal covers a certain level, that means it is beyond a certain level for a certain percentage of time, the error probability is good. Otherwise, if signal is below a certain threshold, we would have outage. So, with slow fading conditions, once the signal goes in outage, it will remain in outage for a longer time, whereas in a fast fading condition the signal fluctuates. So, it goes below the threshold as well as it comes above the threshold. So, that is the other advantage of fast fading or the other disadvantage of slow fading condition, right. So, with this quick description, we would like to move ahead. Okay, we will take this particular picture. So, when we say that the signal is fluctuating as shown in this particular diagram, this particular picture shows signal fluctuating. So, this is the time axis, and this is, let us say, h of t or r tilde of t when s tilde t is equal to 1, right. So, that means when there is continuous wave transmission. So, when we are having this, the signal is fluctuating, and we have also seen one kind of way of describing this. So, when the signal fluctuates, right, the rate of fluctuation is defined. The maximum rate of fluctuation we have already defined it as Fm, which is equal to V by C times Fc. This could be plus or minus depending upon whether the vehicle is approaching the signal or it is moving away from the signal. So, if there is the tower and there is the vehicle, if it is going away, it is minus Fm. If it is going towards this, there is a plus Fm. So, there is a span of plus minus Fm that is present in this particular situation. All other cases, when there is a signal arriving at an angle theta n, we have said f Doppler at a certain angle is equal to theta n. So, that lies between minus theta minus Fm and plus Fm. So, this Fd what we have seen in our earlier derivation gets added to Fc. So, what does it mean? The signal is transmitted at carrier frequency Fc, but when it is coming to the receiver perceives it to be coming at a frequency of Fc plus Fdn. This Fdn could be plus Fm, could be minus Fm, or could be anything in between. So, if there is only one transmitter and there is nothing in the space, absolutely nothing, and this is either moving away in the direction or going towards it, there will be only one value, that is plus Fm or minus Fm, right. So, that means Fc that is transmitted is going to be shifted to Fc plus Fdn, that means Fc plus Fm or minus Fm, nothing else. So, there is only one single frequency. That is also not a problematic case, because the receiver can tune to that particular frequency. That means the receiver considers Fc cap as Fc plus Fdn, which is equal to Fc plus or minus Fm, either of it. So, in this case receiver can tune to this particular frequency and there is no problem. Whereas, when there are multiple paths because of theta, what the receiver sees is multitude of frequencies. This is what we have already seen. That means the receiver is basically getting Fc plus Fdn. It is basically getting a whole set of frequencies. So, this is one view. The other thing which we should consider is when a signal is fluctuating, as I was just mentioning, there is a rate of fluctuation. This fluctuation is mentioned or is described over here by means of Fm. And what we are noting here is there is a plus Fm, there is a minus Fm, and there is a whole range of frequencies in between. What we would like to find out is what are the weights of these frequencies, or what percentage of which frequency is present in the system, or that means we are trying to look at the spectrum of the fluctuation. So, if there is a fluctuation that is happening, what is this frequency content of this fluctuation? That is what we are interested in. Now, since this is a random process, we cannot take a Fourier transform and study it, because a Fourier transform would be of a particular snapshot of a signal. That means, we are reading a particular section of the signal and we are taking the Fourier transform of it, and as time changes, this particular snapshot is going to change. So, the next snapshot for the same process could be this, and naturally the Fourier transform would be different. So, and in the third case, the third time instant, I take the series, it would be different and the Fourier transform would be different. So, what is rather studied is the power spectral density. So, that means you take the Fourier transforms or you take the spectrum of snapshots and then you look at it in an average and you find out what is the average content of signal in it. Now, that could be one way of studying it, but there is also another more effective way of studying it is you take the Fourier transform of the autocorrelation function. If you take the Fourier transform of the autocorrelation function, then also you can arrive at the power spectral density of the fluctuations, because that would give us what is the content of different frequencies that are present in the fluctuations. Now, for us, phi HH delta t is basically phi HI delta t plus j phi HQ HI delta t, where we have seen this component goes to 0 and this component remains as non-zero, and the result for this component is omega p by 2 j 0 2 pi fm delta t. Now, in order to get the Fourier transform of this, so that we get the power spectral density, we would be getting S indicating the power spectral density HI of f is equal to integral of minus infinity to infinity phi HI delta t, it is a function of delta t, e to the power of minus j 2 pi f delta t d of delta t. So, with this we have to expand this particular expression. Now, for phi for j 0, this expression is, that means j 0 of x could be written as 1 by pi 0 to pi cos of x sine theta d theta, or this could be replaced by a cos, or you could also have 2 by pi 0 to pi by 2 cos of x sine theta d theta. This could also be 2 by pi 0 to pi by 2 cos of x cos theta d theta, because the integral between 0 to pi by 2 of sin theta and that of cos theta would be the same, because clearly one is going from 1 to 0, the other is going from 0 to 1. So, the area under the curve won't be different, they would be the same in these cases. So, basically these are the different expressions that we can use. So, we would write this expression as omega p by 2 minus infinity to infinity 2 by pi 0 to pi by 2 cos of 2 pi fm delta t sin theta d theta e to the power of minus j 2 pi f delta t d of delta t. So, with this expression we have to carry forward. So, this would lead us to omega p by 2. Of course, we have to make certain change of variables. We will make sin theta is equal to x, and that would lead to d theta equals to dx by square root of 1 minus x squared. Sin theta would be cos theta d theta equals to dx, and d theta is dx by cos theta. Cos theta is root over 1 minus x squared because of this, and the limit of the integral from 0 to pi by 2 would naturally change to 0 to 1, and what we would have is minus, and we would change the integrals here. So, we could write 0 to 1 2 by pi minus infinity to infinity cos of 2 pi fm delta t of x e to the power of minus j 2 pi f delta t by square root of 1 minus x squared d of delta t dx, and we could continue from that point, and you could do a translation possibly that 2 pi fm delta t equals to y. You could do it this way also, and after one more step it would lead to 0 to 2 pi. I'm keeping all the constants as it is, so that we can take care of them later, and instead of cos we could have e to the power of j y x plus e to the power of minus j y x divided by 2 e to the power of minus y f by fm dy by 2 pi fm with this translation times dx. And if we continue with this, you are going to get, you will have to collect these two terms. So, you will be getting e to the power of j times y x minus f by fm, and you will also be getting e to the power of j times y minus x minus f by fm, and integrated from minus infinity to plus infinity 2 by pi root over 1 minus x squared 1 by 4 pi fm omega p by 2 0 to 1 dy dx. Now, if you look at this integral with dy and this integral with dy, you are going to get a delta function of x minus f by fm, and here you are going to get a delta function of minus x minus f by fm. So, you will be getting two delta functions, and denominator is this. So, your end expression, what you will be left with is omega p by 2 pi fm integral 0 to 1 by root over minus x squared delta x minus f by fm plus delta minus x minus f by fm dx. So, these are valid only for x equals to minus f by fm and x equals to f by fm. So, what you would conclude is this is equal to 1 by 2 pi fm 1 by square root of 1 minus f by fm mod squared, subject to the condition that f by fm is less than or equal to 1, or rather mod of f is less than or equal to fm. So, this is the spectrum of S H H of f, that means the spectrum of the baseband signal. Now, if you try to plot the particular signal over here, what we see is that when f is equal to fm or very close to fm, this value almost tends to infinity. So, if this is 0, this is fm, this is minus fm, there is very high value, and when fm is equal to f is equal to 0, that means this is 1. So, you have some minimal value over here and all values would lie in between. So, what you would have a spectrum which looks like this, that is known as the Jake spectrum, and we will take a look at it. So, the spectrum looks has an expression of this quantity which we have just derived, and if you would look at the passband spectrum. So, the passband spectrum the passband spectrum can be calculated from G is basically H. In our case, we have actually used H, we never used G. So, S H H is equal to this particular expression, that means S H I of f plus J S H Q H I, but now this term would be 0 because this is the Fourier transform of the cross correlation coefficient, which is 0. So, basically this is effectively giving us the entire thing. So, if we would use the previous expression which we derived into this, what we would get is the spectrum in the passband. So, in the passband, the spectrum would look like this. In the baseband, just to remind you, the baseband spectrum would look like omega p by 2 pi fm square root of 1 minus f by fm mod squared mod f is less than or equal to fm. That was the criteria that was set. So, here that gets modified to f minus fc. So, that means fc was set equals to 0. You could also imagine it in that way. So, when it is the baseband, this fc is equal to 0, whereas it in passband fc is not equal to 0, it is present in this particular expression, and the spectrum looks like this. Okay. So, the spectrum looks like the shape that has been drawn over here. So, this is the famous Jake spectrum. This is also known as the Jake spectrum. And again, I would like to remind you, all this derivation is because p of theta was set equal to 1 by 2 pi. If p theta is not set equals to 1 by 2 pi, the expression would look different. P theta being set equals to 1 by 2 pi means rays arriving from all directions with equal probability. So, that inherently means that there is no line of sight, there is no line of sight component present in this situation, because there is equal probability of rays arriving from all directions. That means, the strength of waves from scattered components are all equal. In that case, if there was a line of sight, there will be a specular component which is not present in this particular scenario. So, this is known as the famous Doppler spectrum or the Jake spectrum. We call it the Doppler spectrum because the spectrum is due to Doppler effect, due to mobility effect, and hence it is known as the Doppler spectrum. And this particular shape of the spectrum is known as the Jake spectrum, which appears for p theta equals to 1 by 2 pi, which is again pretty famous. This is observed in reality, although we had derived it analytically. This is observed in reality, and there is a match between observation and the derivation, and that is why this particular model is a very famous model and is the basis for several results in the domain of wireless communications. We have another spectrum here, which is the Gauss spectrum. The Gauss spectrum is here. The corresponding autocorrelation function is here. This again, this particular result is taken from mobile fading channels by Matthias Padzol, and these particular graphs are there. So, for the Gauss spectrum, the spectrum would look like this. if you do the inverse Fourier transform, you would get the autocorrelation function. So, when we arrived at the spectrum, we did the Fourier transform of the autocorrelation function. Similarly, there is also another way of arriving at the autocorrelation function instead of the way we have done, is you arrive at the power spectral density. From power spectral density, you take the inverse Fourier transform and you arrive at the autocorrelation function. So, basically power spectral density, take the inverse Fourier transform, you get correlation function. You do the Fourier transform, you are going to get the power spectral density. So, we have traveled this path, you can travel this path also, but in that case arriving at the power spectral density is not very rigorous, it is kind of through explanations, and but that is pretty satisfying and it is used in many cases. That is a little bit easier compared to the particular process that we have followed in this particular method. Okay. So, we continue with this. Okay. So, now it is important. So, instead of p theta being 1, that is whatever we have said. So, if there is a specular component, and remember specular component we have discussed, and we said whenever p theta is not equal to 1, that means we have a line of sight, we are talking of line of sight, one component being stronger than the other, k is the weight of the line of sight or the specular component. For the distribution, we had talked about Rician distribution. In this case, we will talk about the particular spectrum. So, p theta is the continuous angle of arrival of distribution of the scatter component, and theta 0 is the angle of arrival of the specular component. As you can see, there is a delta theta minus theta 0, delta theta minus theta 0 indicating that there is this much amount of power, ratio of k, there is this much amount of power coming from the theta 0 direction, whereas this is the weight of the power on the scatter components. That means there are rays coming from all directions, and there is a strong specular component which is having this ratio of k is to 1 with respect to all these powers. So, there is a specular component and that is coming at an angle of theta 0. Okay. So, that is what is mentioned by this particular expression. Okay. So, if that is the case, what you are going to get is a complicated expression, the expression for phi gg, that means phi h. So, in our case it is h and not g, in our case it is h. So, wherever there is g, you would treat it as h in whatever we have done. This particular section matches our results for this particular section matches the result for the non line of sight. This is the additional component of line of sight because of this part. Similarly, additionally there is this phi gi gq component which was not present earlier, because remember in this case we have a mean mi and we have a mean mq which were 0 for the case of p theta equals to 1 by 2 pi, is non-zero for this particular case. And this is the power spectral density, and which would look in this fashion as given over here. So, this is for the Rician case, it looks more complicated, and that is why Rayleigh is the case which is more easy and gives us an insight into performance of systems. So, this would result in spectrum as shown in this particular slide. If you have a specular component, this is the Jake spectrum as you can see. So, there is draw on top of it, this is the Jake spectrum, and whereas the Rice spectrum, as because of the Rician distribution, there is this Jake spectrum on top of which there is this strong specular component, right. And what we also have over here is the Gauss spectrum, but as of now what is important for us is the comparison of the Jake spectrum and the Rice spectrum. And these pictures I have actually taken from the book by Matthias Padzol, which is on mobile fading channels. That is also a very famous book. It is a very detailed book. So, if you are interested in studying more about channel model effects, the book by Professor Matthias Padzol, which is on mobile radio channels, is also very well recommended. So, what we remember is when we have the Rician component, the Rician component would mean that there is this strong frequency component, and this is clearly because we have this theta 0 which is giving rise to a particular frequency, and we have f d n is equal to f m cos theta n. In this case this is theta 0. So, basically this is a very strong component. A very strong component means this particular frequency is strong. So, that particular frequency being strong means it is appearing on top of the Jake spectrum. So, the Jake spectrum is here on top of the Jake spectrum, this is clearly visible. So, that is because of the line of sight present or a specular component being present. Okay. So, we stop at this point, and what I would like to tell you is we have covered some of the most important things required to understand wireless communication systems. The rest of the communication systems would build on these things, although we have some more things to cover, but whatever we have done till now is I would underline that they are very, very important. So, I would urge you to go through these parts again and again, so that you understand them thoroughly, because this is not very easy, I would say, because it requires certain visualization. It's not that the maths and other things are very difficult, but it's probably difficult to connect, because we are doing some mathematics over here, whereas what is actually happening in the nature. So, go through the references, look at the materials which are provided, go through the discussions, so that your understanding is improved, because once you understand this, then only your understanding of the rest of the course would be meaningful. Means we will be not referring to this directly, we will assume all the things that we have mentioned over here is well understood. For instance, we will assume slow fading, we will assume fast fading, we will assume flat fading. So, that would clearly ring a bell that we are talking about the spectrum over which the signal is not fluctuating. We are talking about the time over which the signal is not fluctuating. So, that is a very relatively easy condition, but it is also important you understand what happens in other cases, because this lays a foundation to your journey into the domain of wireless communications. Thank you.